Hello, sir.
Welcome to the physics lesson on the topic wave motion and subtopic electromagnetic spectrum. My name is Raphael Mposi. The objectives for the lesson: describing the main component of the electromagnetic spectrum, describe the properties of the waves. Visible light is part of the spectrum. So the visible light we are able to see. There are other parts of the spectrum that we are not able to see. And these components are the ones that we are going to focus on today. May I know if you can give us the main components of the spectrum? What are the main components of the electromagnetic spectrum? Judy?
X-rays.
X-rays. Mwazani?
Ultraviolet rays.
Ultraviolet rays. Christine?
Radio waves.
Radio waves. Grace?
Gamma rays.
Gamma rays. Anastasia?
Infrared.
Infrared. Helen?
Microwaves.
Microwaves. So the components of the electromagnetic spectrum. The components of the electromagnetic spectrum we have mentioned. Microwaves, ultraviolet, infrared, X-rays, gamma rays, radio waves. Which other component is supposed to be on this spectrum? Yes, Miss.
Visible light.
Visible light. Visible light. So these components are supposed to be arranged in order of increasing frequency or in order of increasing wavelength. So we can go to the chart and see the correct order of arrangement of these components. So from here, we have visible light, and as we move towards the right, the next component is ultraviolet, then X-rays, then gamma rays, and when we are moving towards gamma rays, the frequency increases while wavelength decreases. Then from visible light, as you move towards the left, the next component is infrared, followed by microwaves, then we have radio waves. And in this case, as you move towards radio waves, the wavelength increases while the frequency decreases. Now, it may not mean that the radio waves, microwaves, or infrared will remain on the left-hand side of the visible light. It can also be put on the right, meaning that the ultraviolet, X-ray, and gamma can also come on the other side. It's just the same. It will mean the frequency will still increase while the wavelength decreases, and towards radio again, the wavelength will increase while the frequency decreases. But in any case, on the visible light, because visible light is a combination of 7 different lights. Maybe, what are these 7 different lights that make up the visible light? Gloria?
Red light.
Come again?
Red light.
Red light. Anastasia?
Orange light.
Orange light. Given?
Yellow light.
Yellow light. Ongani?
Green light.
Green light. Helen?
Blue light.
Blue light. Christine?
Indigo light.
Indigo light. Grace?
Violet light.
Violet light. So we can also summarize it as Roy GB. So that this gives us the visible light. So that on the end where you have red, it means that the next component will be infrared. On the other end where you have violet, the next one will be ultraviolet. Then it continues. So, components of the spectrum. We can also look at the properties of these electromagnetic waves. What are the properties? What are the properties? Given?
They can travel in a vacuum.
Properties of the electromagnetic waves. They can travel in a vacuum. If they can travel in a vacuum, what could be their speed or velocity? If these waves can travel in a vacuum, what could be their speed? Natasha?
300 million meters per second.
300 million meters per second. They can travel in a vacuum at a speed of 300 million meters per second, or in standard form 3.0 times 10 to the power 8 meters per second. Another property of electromagnetic waves. Grace?
They are transverse waves.
They are transverse waves. They are transverse waves in nature. You can go to the next board. What is meant by a transverse wave? What is meant by a transverse wave? Anastasia?
A transverse wave is a wave in which its particles vibrate perpendicular to the motion of the wave.
Okay. Another property? Given?
They are not charged.
They are?
Not charged.
They are not charged. They are not charged. Can you explain more?
They are not positively or negatively charged.
Okay, Helen?
They are unaffected by electric and magnetic fields.
They are? They are unaffected by an electric field or magnetic field. Another very important property. Misozi?
They transfer energy from one place to another.
They transfer energy from one point to another. They transfer energy from one point to another. Can we get to the last one? So is it?
They obey the wave equation.
They obey
They
the wave equation. They obey the wave equation. Who can give us the wave equation? Which these waves obey? Who can give us the wave equation? Which these waves obey? Yes?
Velocity is equal to frequency times lambda.
So the wave equation links the wave speed, frequency, and wavelength. So wave speed is given by frequency times wavelength. Wave speed is equal to frequency times wavelength. Now, whenever you are dealing with the electromagnetic waves, the speed is already known. the speed is already known. Because earlier on, we said that these waves travel in a vacuum. At what speed? 300 million meters per second. So when you are applying the wave equation in relation to these waves, the speed is already known, which is 3 times 10 to the power 8 meters per second. So that if you are solving a problem, you already know one quantity, which is the speed of the waves. So let's look at an example on how we can apply the wave equation in relation to these waves. So we go back to the other board. Example. A VHF radio station broadcasts a live program at a frequency of 100 megahertz. What is the wavelength of radio waves? So, in order to find a solution to this problem, we know that this station is using radio waves to broadcast the program. And we know that radio waves travel in a vacuum at a speed of 300 million meters per second. So it means we already know the speed. So speed is 3 times 10 to the power 8 meters per second. Which other quantity are we given? So, we are given the frequency. So the frequency is given as 100 megahertz. So because megahertz are not SI units, we need to convert megahertz into hertz. Because the SI units for frequency are hertz, not megahertz. So how do we convert megahertz into hertz?
We say 1 megahertz is equal to 1 million hertz, and then you say 100 megahertz is equal to X, and then you multiply.
Okay, so we look at the conversion factor. So 1 megahertz is equivalent to 10 to the power 6 hertz. Therefore, 100 megahertz is equivalent to Y. If you solve for Y, this will be the frequency in hertz. So what's the frequency in hertz? So
100 million hertz.
So it will be 100 million hertz. In the standard form? In the standard form? Gloria?
1.0 and 10 to the power.
So in standard form it would be 1.0 times 10 to the power 8 hertz. So we have our two quantities that we need to find the wavelength. We have the speed of radio waves, 3 times 10 to the power 8 meters per second. We have also the frequency, which is 1.0 times 10 to the power 8 hertz. Then now, we use the wave equation to solve for the wavelength. So we are going to use the wave equation, which is speed is equal to frequency times wavelength. What we are finding is wavelength. So therefore, wavelength is equal to speed divided by frequency. Then we simply substitute the values in. The speed, 3 times 10 to the power 8 meters per second divided by the frequency, 1.0 times 10 to the power 8 hertz. When dealing with such values, we can borrow the ideas from mathematics, how to deal with the indices when you are dividing and multiplying. So we are dividing, so what do we do to the indices? Subtract. So 8 minus 8?
0.
So this will be 10 to the power 0. What is 10 to the power 0?
1.
So I'm going to say 1 into 3 times 1.
3.
So it means the wavelength will be 3 meters. So this means the wavelength for the radio waves is 3 meters. The wavelength for the radio waves is 3 meters. So I'll give you 2 questions that are going to work out in pairs. So the wavelength of X is 2.0 times 10 to the power 9 meters. Calculate the frequency of X-rays.
Our question is saying the wavelength of X-rays is 2.0 times 10 to the power negative 9 meters. Calculate the frequency of X-rays. So, first of all, we've been given the wavelength. So our wavelength is 2.0 times 10 to the power negative 9 meters. And then we know our speed. We already know our speed. And our speed is equal to 3.0 times 10 to the power 8 meters per second. And then we've been told to find the frequency. We do not know the frequency. So, we're going to use the formula for speed is equal to frequency times wavelength. So since we're finding the frequency, we're going to divide by the wavelength, so that we make the frequency the subject of the formula. So frequency is equal to speed over the wavelength. And then frequency will be equal to our speed is here, which is 3.0 times 10 to the power 8 meters per second over the wavelength will be given 2.0 times 10 to the power -9 meters. And now we're going to, since here if we're dividing the same values, we're going to subtract 8 minus -9. And when we subtract 8 minus -9, negative, positive. 8 plus 9 will give you 17. So this one will give us 3.0 times 10 to the power 17 over 2.0. And then meters, since we're finding our frequency, so we will forget about the values. And then 2 in 3.0 to give you 1.5 times 10 to the power 17. Frequency is measured in hertz, so we're going to put hertz. This will be our frequency.
Okay, so we have captured the main objectives of the lesson, which are looking at the main components of the spectrum and the properties of the electromagnetic spectrum. We have come to the end of the lesson. My name is Raphael Kosi, and on behalf of the studio crew, until next time, it's goodbye.